We've been discussing proof by induction, but what we've actually been doing is something known as weak induction. And in this video, we're going to introduce a refinement of the technique known as strong induction. Here's a problem regarding a sequence with a two-step recursion. A sub 0 is given to be 1, as is a sub 1. A sub 1 is also 1. Once you get past index 0 and 1, you compute the next term of the sequence by taking the term before it plus 2 times the term before that. Okay, so we could go ahead and compute, for example, that a sub 2 is equal to a sub 1 plus 2 times a sub 0, which is 1 plus 2 times 1, or 3. Then a sub 3 is a sub 2 plus 2 times a sub 1, which is going to be 3 plus 2 times 1, or 5. Then a sub 4 is a sub 3 plus 2 times a sub 2, which is 5 plus 2 times 3, or 11, etc., etc. Okay. So we can go ahead and compute terms of the sequence using this two-step recursion. But is there an explicit formula that we can use to compute terms of this sequence? Well, hopefully so. Well, in fact, there is. Okay, what we're going to do is prove that for all natural numbers, a sub n is given by this explicit sequence right here. So we're going to try to prove it by induction because we're trying to prove something for all natural numbers. So for our base case, we're going to use n equals 0 and hope that a sub 0 is negative 1 to the 0 plus 2 to the 0 plus 1 over 3. Well, a sub 0 was given to be equal to 1. Negative 1 to the 0 is 1. 2 to the 0 plus 1 is 2. And indeed, 1 plus 2 over 3 is equal to 1. So a sub 0 does in fact equal what this formula would predict. So the claim is true for n equals 0. Now what we would do, if we're doing a proof by induction as we have seen it before, we would assume that this is true for a given n, and then try to show it's true for the next index. But our inductive formula requires knowledge of two previous terms. Well, if we assume a sub n is given by this formula right here, we multiply it by 2, but we have no idea what to do about a sub n plus 1. We only get to assume, doing a weak inductive proof, that our claim is true for a particular index n. Other indices, like n plus 1, I have no idea. So our recursive formula has two unknown terms in it, and that's not very helpful. So since we didn't get to assume anything about a sub n plus 1, we actually don't know how to compute a sub n plus 2, or vice versa. By not assuming anything about a sub n plus 2, we can't compute a sub n plus 1. So the way to resolve this is a strengthening of the technique called proof by induction, and we call it proof by strong induction. If your claim is true, not just for a particular index, but for all indices up to k, okay? Assuming it's true for all indices up to a certain point, can you derive that it's true for the next index? So in proof by weak induction, you assume the claim is true for a particular index and then try to prove it's true for the next one. In a proof by strong induction, you assume it is true for every index up to a certain point, and then you can derive that it's true for the next one. So you get to make more assumptions, which should make the proof more feasible, but perhaps longer to write. Now, what does this k stand for? This k is the number of base cases that you have to prove. Okay. This is logically equivalent to our earlier form, which is now going to be called weak induction. Having introduced a new technique, we should probably practice it. So let's take a look at an example. Well, it's going to be the example from the previous slide. This is the same recursive formula, and we're going to try to show that the same explicit formula holds for all indices. But we don't have a single base case here. We want to show two separate base cases. How do I know that 2 is the magic number of base cases to show? There are two things to look at here. First, assuming your instructor is not trying to trick you, there were two terms of the sequence explicitly given, a sub 0 and a sub 1. This is a pretty big hint that the indices 0 and 1 are the base cases you want to examine. More accurately, however, look at the recursive formula. If I want to derive information about a specific term of the sequence, I need the term before it and the term before that. In other words, you need to know the value of two consecutive terms in order to get the next one. This tells me that 2 consecutive indices form the base cases that I want, and the first 2 consecutive indices are index 0 and index 1. So those are our 2 base cases, index 0 and index 1. Well, for index 0, we've already verified from the previous slide that the formula holds fine. If the index is 1, we want a sub 1 to equal negative 1 to the first plus 2 to the second over 3. But indeed, negative 1 to the first plus 2 to the second over 3 is negative 1 plus 4 over 3, which is 1, which is exactly the value of a sub 1 that was given to us. So our desired claim does hold true for both indices 0 and 1. We have shown 2 base cases, the first 2 indices, index 0 and index 1. So since the claim is true for these 2 indices, we proceed with a strong inductive proof. We don't just assume the claim is true for some particular natural number. Instead, we assume the claim is true for every index up to capital N, where n is at least as large as the last index used in the base case. So the indices we used for our base case were indices 0 and 1. So we assume there's a capital N at least as large as 1, the last index, and the claim is true for every index up to that point. Now, we're not actually assuming capital N is 1. We're not actually assuming it's anything in particular. We're just assuming it's some number at least as large as the last index of all the base cases, and then assuming the claim is true for every index up to that point. So since we've assumed the claim is true for every index up to n, well, here's our inductive formula for the next term. Compare this to the one that was given here. A sub little n plus 2 is a sub little n plus 1 plus 2 times a sub n. This index is 1 larger than that one, and this index is 1 larger than that one. That's the important relationship. The way it's written isn't so important. It's the relationship between the indices. This index is 1 smaller than this, and this index is 1 smaller than that. So here I have index capital N plus 1 because this is the next term I want to derive something about. Our recursive formula tells us that a term of the sequence is the one before it plus 2 times the one before that. So a sub capital N plus 1 is the term before it, a sub capital N, plus 2 times the one before that, a sub capital N minus 1. Now we assumed our desired formula holds for every index up to n, meaning it doesn't just hold for a sub n matches the desired formula, but it also holds for the previous index a sub n minus 1. Comparing our desired formula, we get a sub n minus 1 equals negative 1 to the n minus 1 plus 2 to the n over 3. Replacing these n's with n minus 1s just means this index is the same as that, and this is 1 larger. So for index n minus 1, we would want negative 1 to the same index, n minus 1, and 2 to 1 larger, which would just be n. So we assumed that this works for a sub n, and this works for a sub n minus 1. And we already see why this is a lot more powerful than weak induction. Because we had multiple assumptions, we can make multiple substitutions, meaning I can utilize this recursive formula that uses many previous terms. And that's also how we see that the number of previous terms really lines up with the number of base cases, so that we can exactly be justified in making assumptions on this many terms of the previous sequence. Okay, so now we have this here. The only trick is, can I do the algebra to make this plus 2 times that what we want, which would be negative 1 to the capital N plus 1 plus 2 to the capital N plus 2 over 3. That would be the desired formula if my index were capital N plus 1. So now it's just an algebra exercise. Well, our common denominator is 3, and it's already there. So if I distribute the 2 across the terms here, we're going to get 2 times negative 1 to the n minus 1. And 2 times 2 to the n is 2 to the n plus 1. I also have a 2 to the n plus 1 here. So something plus itself is 2 times it. So 2 to the n plus 1 plus 2 to the n plus 1 is 2 times 2 to the n plus 1, which is actually just 2 to the n plus 2. So now I've got negative 1 to the capital N, 2 times negative 1 to the n minus 1, and 2 to the n plus 2 all over 3. Okay, so this 2 to the n plus 2 stays the same. Now y is negative 1 to the n plus 2 times negative 1 to the n minus 1 equal to negative 1 to the n minus 1. So negative 1 to the n is actually the same thing as negative 1 times negative 1 to the n minus 1. -1 to the first. This is just playing around with exponents. So observe that we have -1 of this thing plus 2 of the same thing. So -1 of a thing plus 2 of the thing is 1 of the thing. So -1 to the n is the same thing as -1 times -1 to the n minus 1. -1 times this thing plus 2 times the same thing gives me a single one of that thing, whatever it is. Now that's equal to this. Notice the only thing I changed was -1 to the n minus 1 is the same thing as -1 to the n plus 1. Why am I allowed to make that change? Well, this power of n plus 1 versus n minus 1, -1 to a power follows a really nice pattern. It's either 1 or -1 according to whether this exponent is even or odd. N plus 1 is even or odd exactly according to whether n minus 1 is even or odd. So these powers of -1 are equal. -1 to the n plus 1 is always the same thing as -1 to the n minus 1. Either both of these powers are odd, in which case you get a -1 equals -1, or both of these powers are even, in which case you get a 1 equals 1. There's another way to explain this, which is that -1 to the n plus 1 is -1 to the second times -1 to the n minus 1. That's just properties of exponents, okay? X to the n plus 1 is x squared times x to the n minus 1. I would just add these exponents together and get that. But -1 squared is just 1. So this is a handy thing that pops up a lot in these recursive strong inductive proofs. -1 to the n plus 1, -1 to the n minus 1 will always be equal to each other. And we used that here. And we ultimately got that a sub n plus 1 is in fact equal to exactly what this formula would have predicted. So having assumed it's true for index 0 and 1, having proved it's true for index 0 and 1, our base cases, if I assume it's true for every index up to n, it must be true for index n plus 1. So having assumed it's true for every index up to 1, this will tell me it's true for index 2. Having assumed it's true for everything up to index 2, it must be true for index 3. Having assumed it's true for everything up to index 3, it must be true for everything including index 4, and so forth and so forth. That concludes the proof by induction. Now, proof by strong induction is a big leap from proof by weak induction, so more examples will be helpful. Here is a recursively defined sequence. A sub 0 is 1, a sub 1 is 2, and in general, the next term of the sequence is 6 times the previous term minus 8 times the term before that. Show that for all natural numbers, a sub n is in fact 2 to the n. Okay. So the recursive formula involves 2 prior terms. In order to get this term of the sequence, I need the one before it and the one before that. Also, we were given 2 terms of the sequence explicitly, so that's also a pretty big hint that a strong inductive proof with 2 base cases is going to be appropriate. So we check manually, does this formula hold if I use index 0? Is a sub 0 2 to the 0? Well, a sub 0 is 1, which yes, checks out. If I manually use index 1, is a sub 1 2 to the first? Well, 2 to the first is 2, which is what was given as a sub 1. So for index 0 and index 1, everything works just fine. So now let's assume the claim is true for all indices up to and including n, where n is at least as large as 1. Specifically, we get to assume the claim is true for index n and the previous term. By assuming something about a sub n and the previous term, we're going to be able to derive something using the recursive formula about the next term. So let's do that. The recursive formula tells me the next term is 6an minus 8an minus 1. We got to assume not only does the formula hold for index n, so I replace that there, but it also holds for all terms before it. Specifically, index n minus 1 allows me to replace that there. Now 6 is 2 times 3, and I can absorb that 2 into 2 to the n. So 6 times 2 to the n gives me 3 times 2 to the n plus 1. And 8 is 2 times 4, or 2 times 2 squared. So I can absorb that 4 into 2 to the n minus 1 and get 2 to the n plus 1. Now I have 3 times a thing minus 2 times the same thing. 3x minus 2x is just x. So ultimately, a sub n plus 1 is in fact 2 to the n plus 1. So the base cases establish the claim is true for the first 2 indices, 0 and 1. Our inductive step says, if it's true for all indices up to n, it must be true for index n plus 1. That concludes the proof by strong induction. Since it's true for everything up to index 1, it must be true including index 2. Since it's now true for everything up to index 2, it must be true for index 3, and so forth and so forth. These proofs tend to follow a pretty predictable pattern. The big stumbling blocks that you have to be careful of are your algebra skills. Can you follow this right here? Honestly, that's the biggest one. Also, can you recognize the difference between a weak inductive proof and a strong inductive proof? And typically at this stage in your mathematical careers, no one is actively trying to trick you. If you have a recursive formula that involves multiple previous terms, you need strong induction. If you have a recursive formula that only uses one previous term, well then weak induction might work just fine. More examples are good. So here is a sequence where r sub 0, r sub 1, and r sub 2 are all equal to 1. And here is our recursive formula. Notice that I need 3 prior terms to get the next one. The claim is nice and straightforward. The claim is that for all indices, r sub n equals 1. But this recursive formula uses 3 prior terms. So we need 3 base cases. Okay, because the recursive formula needs us to look back 3 steps into the past, we're going to need 3 base cases. Now, the nice thing is that the formula r sub n equals 1 is very easy to check. Is r sub 0 equal to 1? Yes. Is r sub 1 equal to 1? Yes. Is r sub 2 equal to 1? Yes. Okay, hooray. The first 3 indices, the desired claim is true, and there was really not any work to be done. We just had to verify, yes. Replacing n with 0, 1, or 2, all equal to 1 was given information, so our claim is true for the first 3 indices. Now what we do is we assume that every term of the sequence is equal to 1 up to n, where n is at least as large as the last index of the base cases, which was 2. What we now need to show is that the claim holds for the next index, that r sub n plus 1 is also equal to 1. A common mistake would be to think we want a 2 here or something, but this is not n or n plus 1, this is just 1. So if I replace n with n plus 1, this is still just a 1. So, since n is at least as large as 2, all of these terms of the sequence exist, and also we assumed they were all equal to 1. So we can use our recursive formula. We just have to adjust the indices in it. This index is 1 larger than this one, is 1 larger than this one, is 1 larger than this one. So the next term of the sequence, rn plus 1, is 4 times the previous term, r sub n, plus 5 times the one before that, which is now index n minus 1, minus 8 times the one before that, which is now index n minus 2. Okay, it's a very common point of confusion. This line and this one are the same thing. The indices are written different, but that's not important. The relationship between the indices is what really matters for these recursive formulas. This index is 1 larger than this one, is 1 larger than this one, is 1 larger than this one. This index is 1 larger than this one, is 1 larger than this one, is 1 larger than this one. It's the same formula. Now, since we assumed all of these are equal to 1, this is 4 times 1, 5 times 1, 8 times 1, 4 plus 5 minus 8, that's just 1. So having assumed that 3 consecutive terms satisfy the desired formula, the next one must as well. That concludes the proof by strong induction. Because the recursive formula involved looking 3 steps in the past, we had 3 base cases, index 0, 1, and 2. So if I assume that 3 consecutive terms follow the desired formula, we were able to derive the next one must as well. Now in this particular problem, the formula was really straightforward. It was just 1. There wasn't much to compute. So we were given a bit of a break here. While this was a 3-step recursive formula, the formula was so simple to check in the end that there wasn't a lot of work to do. It was just getting used to the idea that you might need more than 2 base cases. You might need 3, you might need 4. Heck, you might need 95. Okay? The technique is fundamentally the same. So in general, how many base cases do you need? What you really want to do is whatever the recursive formula is, look how many terms in the past it goes. To get this index, I need 3 steps back. To get index n plus 3, I need to look all the way back 3 steps to index n. That tells me I need 3 base cases, or index 0, index 1, index 2. Okay, let's look at an explicit form for the Fibonacci numbers f sub n. Remember that the Fibonacci terms were given as follows. F sub 0 is 0, f sub 1 is 1. And then we've got a very straightforward two-step recursive formula. One term is equal to the term before it plus the term before that. We're going to prove Benet's formula. This was mentioned in a previous slide, that the Fibonacci numbers can be explicitly computed as, this is the Greek letter phi or phi to the n minus the Greek letter psi, psi, to the n. So phi to the n minus psi to the n over root 5, where specifically the Greek letter phi is a specific number. It's 1 plus root 5 over 2. This is also called the golden mean or the golden ratio or the golden section. And psi is 1 minus root 5 over 2. So the two base cases are actually pretty easy to establish. Okay, we know there's two base cases because our recursive formula looks 2 steps into the past. So f sub 0 was just given to be 0. If I compute phi to the 0 minus psi to the 0, well, while these numbers are complicated, raising them to the 0 power is pretty straightforward. It's 1 minus 1. Who cares about the denominator? That is in fact equal to 0. So yes, f sub 0 is 0, which does match the desired formula. For index 1, it's a little tedious. Okay, phi to the first would be 1 plus root 5 over 2, minus psi to the first, 1 minus root 5 over 2. Notice this 1/2 will exactly cancel this 1/2, and then I'll have root 5 plus root 5, or 2 root 5 over 2, all over root 5. So I get 2 root 5 over 2 root 5, which is 1, which is exactly the value of f sub 1 that was given. So while it did take a little bit of computation, we were able to verify that the explicit formula, Benet's formula, holds for index 0 and for index 1. Now we get to assume that it holds for all indices up to some n at least as large as 1, the last index that we proved in the base cases. Then we can proceed with the inductive step. So our recursive formula tells me a term of the sequence is the one before it plus the one before that. And if I adjust my indices, we get f sub n plus 1 is fn plus fn minus 1. Now fn was assumed to follow Benet's formula. So phi to the n minus psi to the n over root 5. But fn minus 1 was also assumed to follow Benet's formula. So phi to the n minus 1 minus psi to the n minus 1 over root 5. All right, continuing from the prior slide, here was our recursive formula for the Fibonacci numbers. Now we assumed f sub n follows Benet's formula, and we also assumed f sub n minus 1 follows Benet's formula. Observe that we have a common denominator of root 5, so I get phi to the n plus phi to the n minus 1, and I get a minus psi to the n and a minus psi to the n minus 1. If I factor a negative 1 out of both of those terms, it's a psi to the n plus psi to the n minus 1. From this parenthetical term, I can factor out phi to the n minus 1, leaving behind phi to the first and phi to the 0, or just 1. And from this parenthetical term, I can also factor out psi to the n minus 1, leaving behind psi plus 1. Now here were the two values of phi and psi. It's a straightforward computation that you should verify, that psi plus 1 is equal to psi squared, and phi plus 1 is equal to phi squared. You can also see this by observing that if you take the formula x squared equals x plus 1 and solve it via the quadratic equation, you'll get x is equal to 1 plus or minus root 5 over 2, which are exactly 1 plus root 5 over 2 is phi, and 1 minus root 5 over 2 is psi. So those two values are exactly the solutions to x squared equals x plus 1. So phi squared is phi plus 1, and psi squared is psi plus 1. So we're going to come up here and replace phi plus 1 with phi squared, and replace psi plus 1 with psi squared. If I do that, fn plus 1 is given by phi to the n minus 1 times phi squared, minus psi to the n minus 1 times psi squared. But now I can combine these two terms, and I can combine these two terms to just get phi to the n plus 1. Notice I'm just combining the exponents. N minus 1 plus 2 gives me n plus 1. N minus 1 plus 2 gives me n plus 1. So I get phi to the n plus 1 minus psi to the n plus 1 over root 5, which is exactly what Binet's formula would have predicted for index n plus 1. So having assumed that Binet's formula held for 2 consecutive indices, we were able to prove it must hold for the next one. Combine that with our base cases that it does hold for 2 consecutive indices, index 0 and index 1, and our strong inductive proof is complete. Binet's formula holds for every natural number. We can compute the Fibonacci numbers through a nice explicit formula. Well, nice in big air quotes. It does involve phi to the n and psi to the n, where those are these numbers here.